Hello, everyone. Welcome to FAT on Chain podcast. Today, I'm with Yannik Schrade from Arcium, and we will discuss, in general, confidential compute, MPC, and what Arcium does. So, Yannik, welcome. It would it would be great if you could, explain some things about your background, who you are, who you're coming from. So, yeah.
Yeah, thanks for having me, Furkan. Super exciting to have this conversation. So, yeah, I'm one of the co-founders and CEO at Arcium, and with Arcium, we are building the encrypted supercomputer. And what it allows for is for generalized confidential computing to be executed both on blockchain networks, so on blockchains that by default are fully transparent, and every single bit of information that is being used in transactions and stored in state is publicly exposed to the prying eyes of everyone. Whereas when using Arcium in a composable way, I guess, on these networks, it now becomes possible to have private state and not only have private state and private execution, but be able to execute over encrypted shared state, if you will. So everyone can have their private information, can have their private data, their sensitive data, and collectively, by using smart contracts, they are able to compute over all of this data without ever having to share any of that data. So that's one of the big things that we are trying to enable with Arcium, and both for on-chain applications. So I think the most straightforward thing there would be confidential DeFi, but also at the same time for machine learning applications. So in the context of that, what we did mid of last year is we acquired our largest Web2 competitor who've been doing this kind of confidential machine learning for more than 8 years for traditional industries. And we're bringing all of that in this permissionless setting where anyone can access this technology, anyone can access this encrypted supercomputer. And yeah, my personal background is in mathematics and computer science, but I guess funnily enough, I also studied law before studying math and computer science. So a bit of a curvy road to where I'm at right now.
Sounds super interesting. Like, first of all, I'm also a mathematician. Like, I mean, I will graduate this year, but yeah, I'll be a mathematician then. Look, yeah, it's super cool. Like, to have that kind of name, like, encrypted supercomputer. I think it's a great name. And yeah, of course, we will discuss further. So yeah, like you did actually a bit, but I would love to see and hear the details regarding Arcium. So how would you describe Arcium in more details for those who are not familiar with?
So really how you can imagine how Arcium functions on its own is that there's, similarly to how blockchains function, there's nodes, computers that are globally distributed, and those nodes don't produce blocks or do the normal tasks that nodes within a blockchain network execute, but instead they execute confidential computations. And the way they do that is through cryptographic primitive called secure multi-party computation. And so there's those nodes within Arcium, and all of the nodes within Arcium are being partitioned into computation clusters, and then those computation clusters run those multi-party computations. And those multi-party computations then allow to operate computations over data without the nodes that run those computations seeing that data. And Arcium is then getting connected, I guess, to blockchain networks by those blockchain networks. And the first blockchain network that we are supporting, currently we are in private testnet and moving into public testnet, is Solana. And so on these blockchain networks, you have smart contracts, and those smart contracts basically function as coordination and entry points into Arcium. So you can on-chain schedule some confidential computations that should be executed within Arcium. And those confidential computations usually are being scheduled by other smart contracts. So let's say you're a developer that wants to build a dark pool. So you want people to be able to trade without revealing their trading strategies, right? Or having MEV protection, not being front run. So when you want to build something like this with Arcium, how it looks like is you basically within your smart contract simply have to specify what functions should be executed in a confidential way and what state should be private. And then our compiler, Arcus, takes care of that, so you don't have to worry too much about understanding cryptographic principles. And what happens under the hood when someone now calls some function that should be executed in a private way on a public blockchain, which is super strange, I guess, right? Once that happens, what actually happens is that your smart contract calls the Arcium smart contract, and simultaneously that gets picked up by the Arcium network. It runs the dedicated computation it should execute and settles that back. And once it's settled back, there's a callback that is being triggered within your smart contract. So the way you can imagine it is sort of like asynchronous confidential execution. And that's it on a very, very high level. But that's what you can do with it, and that's incredibly powerful. And that means that you can now build applications where you add privacy, add confidentiality, just as if you, I don't know, were to rent a server or build a server in your basement and protect that server, so nobody had access to that server. But now you can just do that on chain. You don't need any trusted infrastructure. I think that's key of what we are trying to achieve. We don't want to rely on any single points of failure. We don't want to rely on any single trusted actors. We want this form of privacy that can be run in a distributed open setting without having to trust some third parties, which is something that I guess is impossible in this framework, right? To actually have someone you can trust your data with.
Thank you. I think it was a really good explanation. I would like to understand the main architecture of Arcium. But like just to make the picture more clear for our viewers, like you mentioned that like the chain you're supporting is Solana. So here is Arcium a sort of L2 or like a different layer, providing confidentiality as a service to Solana apps?
So Arcium definitely isn't an L2, simply because, and that's also one of the big conscious design decisions that we undertook with Arcium. We were at this point where we said, okay, are we gonna be spinning up our own L1, our own blockchain, where then people can go and build private applications, right? And I think that's nonsense. I think that's a very bad approach. I think privacy, confidentiality, confidential computing should be at the fingertips of developers, should be where the most powerful applications are being built, right? And so with that requirement in mind, the architecture also isn't an L2, because that would mean that, I don't know, you would have to move something to Arcium, but it's basically just if you're thinking in this model that Solana is on-chain, then it's just off-chain compute that is being settled back, right? That's the way I would describe it, but it's difficult to actually to classify. It's a difficult task because it's not like you just have those nodes like with, I guess, some proving network or something like that, where you can just outsource something and it comes back. But instead it's more nuanced, because you require those nodes to actually run certain computations, simply due to the cryptography involved, right? So you require some specific set of nodes to run a computation, and you require that to be performed in a censorship resistant way, right? So we require censorship resistance for our network, but we're not a blockchain network. So that by nature is a difficult task, and how we solve that is by implementing some new censorship resistance mechanisms into our cryptography. And that namely means that we have so-called cheater identification, identifiable abort within the MPC protocol, which, if some node in a computation causes the computation to fail, which would be a normal censorship action, which this node could cause through non-participation or just within this mathematical cryptographic operation, sharing some invalid data, which then causes the computation to fail. And with this new protocol, we're able to actually cryptographically identify and pinpoint them and then punish them, which is then a task that is being performed again on Solana in the example of Solana. So I think that makes it even a bit more difficult, because it's not just, hey, we have this off-chain network that runs some computations, where we have this off-chain network that runs computations, but it also needs sort of the same level of censorship resistance, right? And so that makes it difficult to classify what kind of network it is. And that's why it's actually an encrypted supercomputer.
Thank you. This wasn't one of the questions in my list, but it's a follow up. In FHE, even though it's still quite early, we're talking about verifiability. So how verifiability is ensured with an MPC? I'm not asking this in the scope of Arcium, but in a general way. So is there also a verifiability problem in MPC, or MPC solves it, in a natural way? It would be good to discuss on that as well.
So within MPC, there's multiple approaches. In MPC, you usually call it public auditability. There's this amazing set of terms where in cryptography there's 10 very similar terms that sort of describe the same thing. But regarding public auditability, it really depends on the protocol. So there's something called collaborative CK snarks, which basically is running a multi-party computation and choosing a protocol and I guess choosing a field and pairings that allow you to produce zero knowledge proof without having to put the zero knowledge proof into the circuit, right? So you just execute some confidential computation, and the output that is being produced is a verifiable output. And what's really interesting is how nicely that fits with MPC protocol. So, for example, with the Speeds MPC protocol, which operates in the dishonest majority, to produce a Groth16 proof, which I guess is the most common proving scheme still up to date, that only introduces an overhead of a factor of 2, right? So it's twice as expensive, which is amazing if you think about you having this cryptographic operation and slapping another cryptographic operation on top of it, which both comes with its costs, but combining them together actually doesn't significantly improve the overhead. So I think that's a very nice characteristic. And there's different kinds of schemes. There's schemes that rely on some trust assumption, which for verifiability sort of doesn't make sense. But in that example, you can produce verifiability in a really nice way. But I think there's multiple aspects to accountability in that setting where you actually manage some keys. So you also have to ensure that you not only produce some verifiable output, but you also have to introduce mechanisms to reduce a trust assumption regarding some secret keys being put together to decrypt information is near to zero or is relative zero. And so that's what we are trying to achieve with Arcium. And now that I say that out loud, that sounds super confusing and super complex. So maybe I can try to explain that, and can try to explain how multi-party computation works. It's
But
relatively
before that one, as far as I know, these cold snarks are quite new things, in verifiable compute. So is it something like already implemented within Arcium, which I mean, it would be a like, tough task because it's, as I said, it's a really new technology. But like, what I'm wondering is, are you like seriously considering to implement any verifiability mechanism into your architecture? Like, I mean, this is of course a personal take, but like, I really care about verifiability. Like, even though it's a nightmare for what I'm studying. But yeah, this is like my generic question for all
What what
PhD
what
workers.
what was your take? You don't care? You
No,
care?
no, I care
Yeah.
maybe too much.
Yeah. So no, that's something that we are actively working on. Yeah.
That I mean, that's great. That's great to hear. So yeah, like you were gonna start talking about
Yeah.
MPC. Yeah.
So MPC is interesting because what you're doing basically is you have some secret value, and other people have secret values, and you want to compute something across all of those secret values as if there was this imaginary party that had access to all of those secret values. But the big problem is there's no such party. There's no third party we can just give all of our values to, and it produces those magical outputs. So what we have instead is mathematics, right? And so for secure multi-party computation, how it functions is that everyone who has a secret um, assembles in this computation. So we have some number of participants. Let's say we have 10 participants, and each single participant has their secret. So now what everybody does is they generate some random data. And that random data has the constraint that it has to be enough random data so that you can give every other participant a bit of that random data. And all of that random data put together should form your secret. And what that means is that when everybody does that, everybody generates those random secret shares and sends them to each other. Everybody ends up with this heap of random data from which you're not able to learn anything about the actual secrets that all the other participants hold, because you just have this heap of random data. One piece of random data that you kept for yourself from your secret, and all of the other 9 random elements that all of the other participants gave you, right? That's this setup that's being used within multi-party computation. And what's really nice is that if we use addition for the secret sharing with a modulus operation, we can be certain that as long as there's one participant who's not, I guess, maliciously collaborating with all of the others, we can have certainty that those secrets remain safe, remain private. And that's trust assumptions, trust models. Being able to only have to trust that there's one honest player or more than half are honest. There's different models, but within MPC, once everyone has access to this heap of random information, everyone can run computations and can make use of what FHE also makes use of, homomorphisms, right? And so you are able to run local operations, and then a subset of operations are being performed based on communication with all of the peers. So everybody just has this heap of random data and computes on it, and then exchange some intermediary results, continuous computing, and then at the end, the output is being produced by then reassembling all of the resulting random data. And that's the secret of MPC. And for these kinds of models, there's trust assumptions associated, and what we operate on in Arcium is the dishonest majority trust assumption, which means regardless how large your set is, if it's 2 players or if it's 1,000 players, you only have to trust that there's one player not maliciously collaborating with all of the others, which in the case of you having at least some skin in the game, running the computation brings you to this zero trust assumption. Yeah. So that's MPC 101, I guess.
Yeah, it was quite good. Like what I'm wondering is like when I see some protocols doing it like doing MPC or utilizing MPC, like a few of them or like maybe more of them, I don't know. Like they when they explain the workflow of like their protocol and like especially the MPC part, I usually see a a step where they like they mention it as encryption, which I'm not sure, like if encryption actually takes place in any step of MPC. Because I mean, how would you compute on encrypted data without FHE? So like, if like
Yeah, yeah.
I'm wondering if this is a clickbait or it's a real, it's a real
Yeah.
aspect.
So most folks when speaking about encryption, what they mean is secret sharing in many cases, right? And secret sharing is you have some data X, and that data X is being split into n random values, and some function over those n random values will give you back X. So that's what many people talk about. But what we're doing at Arcium, for example, is you have you encrypt your data, so you have some information that you want to compute on. I have some information I want to compute on, and I want that Arcium runs on both of our information. So what both of us are doing is we encrypt we with a public key, and both of us encrypt that data. And then the computing cluster that runs the secure multi-party computation, what it does is it transforms this encrypted representation into the secret shared representation without ever decrypting it. And MPC always has to operate over the secret shared representation, which I think it's not correct to call it encrypt to be encrypted, right? But in the case of Arcium, it's we actually operate over this ciphertext because it's being transformed into the computation, and then at the end it's transformed again into a ciphertext without having a plain text representation in between. And the operations that are being executed are that for additions, the protocol, and that's what most SHE protocols make use of, is that the additions are being performed homomorphically, and for the multiplications, they make use of pre-processing with correlated randomness, which then eliminates the requirement for bootstrapping.
Yeah, yeah, with quite explanatory. So like you mentioned several times about like clusters, and like as far as I know, Arcium architecture has arc nodes and clusters. So how they differ, or like what's the significance of each? It would be great if you could elaborate on that.
Yeah, sure. So as I said, Arcium really is this open network of all different kinds of nodes. So basically, there's no hardware constraint on running a node within Arcium. At the same time, when you run a multi-party computation, or you deploy a program that should have some confidential execution, you basically specify a cluster of nodes that is somewhat persistent, I guess, that should run those computations. So a cluster is just a set of arcs nodes, and I guess some rules defining how replacement and migration of nodes can take place within that cluster. And in order to become part of such a cluster, you basically are being invited to join some cluster and being assigned the computation tasks to some program. And in order for you as a node provider to be able to be in 1 million clusters and process 1 million computations simultaneously, you need to stake corresponding to that, because the dependence of all of those clusters on you is higher. Because as I outlined earlier, we have the censorship resistance requirement, and the censorship resistance mechanism slashes censorship actions, right? And so that's why whatever your hardware specs are, you need to unlock those basically through staking or delegated stake, and then you're able to process these kinds of confidential computations.
Yeah, so like, are these clusters, dedicated to some particular compute, or can they be used for different computations?
Yeah, they can be used for different computations. So you can have a cluster that is associated with, let's say, 1,000 smart contracts, and one of those smart contracts has a computation every second. One has a computation every week. I don't know, something like that, right? So they can process all of those different things asynchronously without having to synchronize on any of those. You can also have a cluster that is specialized to machine learning, because all of the ARCs nodes within have the corresponding hardware that allows them to offer the fastest confidential operations for the Manticore protocol, which we got through acquiring Infer. And so there can really be the specialization for node operators. There can really be the node operator saying, hey, I'm optimizing my servers for performance. I'm optimizing my servers for this kind of use case, this kind of protocol, because I can keep so much in memory that I can allow for this enormous order book to be processed in my computations or other nodes, specializing more on the machine learning front.
Like, honestly, I really like this approach because, like, instead of using the entire network for like dozens of different use cases, like scaling vertically and like having different clusters for different kinds of computational compute, confidential compute would like seems like wiser, even though I don't know about like benchmarks or like how they actually does work under hood, but like it's like similar to like app chains, but this time, use case specific clusters. And like, I'm wondering how much they differ from, like, let's say we have a cluster for confidential machine learning and another cluster for, let's say, dark pools. So what kind of different properties these two different clusters have?
Yeah, that's a great question. So the cluster can differ also in their size, right? You can have a use case where you say, okay, I want to have 100 nodes. Then you have a use case where you say, hey, um, actually, I'm fine with a bit higher trust assumption because for reason X, Y, Z, and that's why I want to have a smaller cluster, which leads to very interesting workflows that can actually be created in that sense, right? We then can say, okay, what if we run this inference and we start off with this very large cluster, where after the first data transformation, I guess, it's abstracted enough that you can't really learn any valuable information anymore. That's why after this part of the computation is being performed, it's being pipelined into smaller clusters, right? Things like that. So I think that can really lead to some interesting constructions down the line. I don't know if it will actually be that case or everything just, I don't know if everything within Arcium will be processed within one cluster. I don't know, but I really see it that way, where it allows for the nodes to specialize, and it becomes this open market, if you will, that incentivizes decentralization already through the stake delegation mechanism as well. Yeah.
Yeah, it was a really nice discussion around the architecture of Arcium. So like this one is more related to MPC in general, and like one of the main concerns regarding MPC is like the scalability, in like in longer terms. So like is like MPC like or like efficiency of MPC is really limited to like speed of light, and then when like let's say after the possible mass adoption happens and like millions of people start using confidential compute on chain, and like will MPC networks could handle all these overhead, or is there some wise solutions for this?
Yeah, so scalability-wise, there's multiple aspects to it. One aspect is by being able to operate in the dishonest majority trust assumption in our example. What it means is that, and I mean, for everyone listening, what Furkan is referring to is that within MPC, MPC is so many is I guess many orders of magnitude faster than FHE, which comes from, for example, using that pre-processing I was referring to earlier. So generating correlated randomness in pre-processing, which then eliminates the need for performing local homomorphic multiplications, and instead being able to use this correlated randomness, which in itself is basically two random factors and the correlated product, and making use of that within the actual multiplication in the circuit. So but that requires then communication, because you first generate some values and then you reveal some values. So it's basically those intermediary revealing steps where values are being opened to all participants, which requires communication. Anyway, so there's multiple aspects to that. One is trying to have as little the smallest set possible of computing nodes, right, in such a computation. And when you, for example, operate in the honest majority trust assumption, that's very problematic, because similarly to how blockchain networks function, right, when you have to trust that more than half are honest, well, then you better have some incredibly large set of nodes, right, which then can lead to the costs exploding. When you operate in dishonest majority, that's different, because you only have to trust that there's one honest participant, and depending on the use case of the computation and the participants, that can be brought down significantly. Another aspect is that regarding network communication, there's different concepts, like last year we've seen packed secret sharing emerge, which allows to basically bring down the network communication costs significantly within those protocols. So I think down the line we will see even more improvements on that front, and any kind of hardware acceleration on its own also benefits those local operations that are being performed within MPC. So I think that's the future we are heading towards.
Yeah, thank you. And like I totally agree. So like in terms of like PET solutions like MPC, FHE, ZK, and maybe even T's. Like I'm wondering what you think on the current status and maybe the future of confidential compute. Like because like some people think like most people even like don't even care about privacy, like in especially Web 2 and even in Web 3. Do you think this will change? When, if so, how?
So I think what's important is that we cannot really build upon the individuals to say, hey, the individuals should care about privacy, and that's why we hope that this kind of technology is gonna find adoption. That's the wrong approach. And also I think that's why we're at Arcium calling it Privacy 2.0. Privacy 1.0 had this wrong approach of framing it as this exclusively political issue. For reason X, Y, and Z, to protect humanity or whatever, we need to have privacy, right? Which is true. You can't deny that. But by simply framing it always as this purely idealistic thing, I think that has hindered adoption and has not allowed us to focus actually on what matters. And what the only thing that really matters is being able to build more powerful applications with this technology. That's it, right? And so that's where being able to actually compute in a confidential way, being actually able to operate over encrypted shared state, right? Being able to train some AI models over highly sensitive healthcare data that is being that's existing in a distributed, encrypted way where nobody has to share anything. That's incredibly valuable, right? So those are entirely new use cases that emerge. And that's something that needs to be communicated and needs to be demonstrated, and then we'll find adoption. So that's what I think about it. And regarding the individual technologies, I think we've really seen this trend that I don't know, zero knowledge proofs don't allow for confidential computing, right? Because that becomes very messy if you need to perform some interactive key exchanges with all potential participants. So I think that was really this evolutionary first step, this introduction of zero knowledge proofs into our space, and yeah, down the line we will see actual confidential computing taking place. Regarding TEEs, I think it's somewhat important to clearly enough separate FHE and MPC and CK from what TEEs offer, because TEEs sort of to me fall in a somewhat different category. If we combine TEEs with all of those three or some of those three technologies, there can be very nice systems. But if we just have a TEE, a single trusted computing platform, and put all of our data in that platform or our keys to our assets, all of that will get lost and stolen, because that's what has happened in the past and will happen in the future. So yeah, in general, confidential computing has a great future ahead, because the narrative has really shifted towards building more powerful applications instead of going around and saying you have to add privacy to the blockchains, because otherwise humanity will suffer, right?
Yeah, it's good to know that we both hate trust.
Yeah.
But like the interesting thing, you think, like, if I understood correctly, like you believe that the supply will create a demand for privacy. Like
so I think supply will create demand. I don't really think that's the case. I think there is demand, but in the past there wasn't any supply, because if you said, "Hey, I want privacy," and then there's some, I don't know, you have a protocol, you have some DeFi protocol that says, "Oh, I would love if we could offer confidential markets, right? Some dark pool," or the end user says, "Man, I would love it if I had MEV protection." I think there's everywhere you look, there's demand for privacy. The problem really has been that never in the past we've seen any technology really match that need. So I think we are really moving towards this point. I think within our space, you can really feel it, where we've had those, I don't know, dedicated CK chains, which nobody ended up using because, as I described earlier, they suffer from this big problem of saying, "Hey, come to our chain and have privacy," but the privacy is sort of fruitless and makes it slower. I think we really have to address the needs of the protocols where they're at, and do that step by step, and we can finally do so.
Yeah, thanks for the clarification, and I think it's more clear now. Before concluding the episode, would you recommend any book for our viewers? Like, it could be about anything, and it will be a generic question for all the episodes. So yeah, I would love to hear. It's like, it doesn't have to be your favorite, but like any book you would recommend.
So I definitely in this podcast have to recommend, because most podcasts I'm part of, if I'm recommending some cryptography book, I'm almost certain that nobody's gonna buy that book. But Real World Cryptography by my good friend David Wong, I think that's an excellent book. yeah, I think that's the most important book I can
Yeah,
recommend everyone.
I totally agree. Like it's actually, I mean, like I had recommended that book to one of my friends who wants to get started with cryptography, and like it's a really great way to start with, understand the basics of, like hard problem assumption,
Yeah,
like keys, encryption, decryption, encoding, decoding, and the other things.
and from an ethical standpoint, I have to promote David's book all the time, because when I read it the first time, I might not have bought it. So yeah.
Thank you. So do you have any final words, or we can conclude?
Yeah, I think what everyone can take away from this conversation is that um, we are moving towards really privacy 2.0, where you can have better apps and you can have privacy without even having to notice it, without you having to care about it, because so many teams and so many smart people have spent a lot of thought over the last few years, blood, sweat, and tears, to building those systems, and we haven't fully reached that point yet. But I think we can really feel the trajectory, and so within the next few years, we will see those ecosystems and networks really adopt this technology and change based on that.
Yeah, thank you. I totally agree. And like also, thanks for being with me today. It was a really nice conversation. We had met in Brussels, I believe, like last summer in FHE
Oh
summit.
yes, yeah,
Yeah.
yeah, yeah. Exactly,
No,
yeah.
yeah,
After,
my
yeah,
talk was right after yours.
yeah, yeah, yeah.
Yeah, and it's good to meet you
Yeah.
again.
No, that was a good event. Yeah, yeah. I think we briefly talked about nomenclature at that point
Yeah,
of SHE.
yeah, yeah. Good memories.
Yeah.
So yeah,
All right.
like,
Yeah. Thanks for having me, Furkan. Always a pleasure.
yeah, sure. I wish we will meet once again, like in one of the events, or even maybe in the podcast again. So yeah. So
Definitely.
yeah. So everyone, today Yannik Schrade was with us in FHE on Chain podcast. We briefly discussed about pretty much everything regarding confidential compute, MPCs, and like of course Arcium's architecture. I hope it was fun and instructive. So thanks for watching.
Bye bye.